The night sky conceals patterns that only emerge when we watch carefully enough. Throughout the autumn of 2025, something peculiar has been unfolding in the darkness beyond our atmosphere, a phenomenon so unexpected that astronomers worldwide are quietly revising their assumptions about how the cosmos operates. As the interstellar visitor designated 3I Atlas continues its arc through our planetary neighborhood, observers have documented an extraordinary clustering of additional objects, all appearing within a time frame so compressed it defies the ordinary rhythms of celestial discovery. This isn't the gradual accumulation of cometary findings spread across seasons and years. This is synchronization on a scale that demands explanation. If this mystery has captured your imagination, as it has captivated researchers around the globe, take a moment to engage with this exploration. Your interaction helps ensure these investigations reach others who seek understanding of our cosmic surroundings. Share your location and thoughts in the comments, and consider spreading this documentary through your networks. Your participation creates the foundation that allows deeper inquiry into phenomena that challenge our frameworks. Tonight's journey takes us through observational data, theoretical models, and the growing realization that 3I Atlas may not be traveling through our solar system alone. By the conclusion of this examination, you'll comprehend why certain scientists are describing this pattern as potentially transformative for our understanding of how interstellar objects interact with planetary systems, and why the coming weeks may provide answers to questions we're only now learning to formulate properly. The narrative begins with 3I Atlas itself, officially catalogued as C2025N1, marking the third confirmed interstellar visitor to our solar system following the famous Oumuamua that appeared in 2017 and the comet Borisov that followed in 2019. Unlike those solitary predecessors, this new arrival has coincided with something unprecedented. Since early detection in July 2025, astronomical survey programs have recorded an explosion of newly visible objects emerging from the outer solar system, all converging toward the interplanetary region during the precise period when 3I Atlas makes its closest approach to our Sun. The numbers tell a story that statistical analysis struggles to categorize as routine. During typical years, major survey programs identify perhaps 4 to 6 comets that brighten sufficiently for detailed characterization. The year 2025 has shattered those expectations dramatically. Current catalogs list at minimum 19 distinct objects that have manifested from the distant reaches, all progressing inward during the identical time frame when 3I Atlas executes its solar passage. These aren't marginal detections hovering at the threshold of visibility. Many represent substantial bodies displaying robust outgassing, prominent comas extending millions of kilometers, and in numerous cases, spectacular tails that stream across the darkness like cosmic banners announcing their presence. The roster reads like a celestial congregation, assembling for purposes unknown. C2025 R3 Swan, C2025 A7 Lemon, C2025 K2 Atlas, accompanied by periodic comets including 415P and 211P that have returned according to schedule, yet exhibit unusual vigor for their orbital positions. What transforms this enumeration from interesting to extraordinary isn't merely the quantity, but the temporal precision. When researchers plot the perihelion dates of these objects, those moments when each reaches its nearest point to the Sun, they construct a histogram displaying a pronounced concentration centered on late 2025, extending into early 2026. Dr. Elena Martinez, a planetary dynamics specialist at the Instituto de Astrofísica in Chile, who has been monitoring this development, characterizes it as divergent from anything preserved in the observational record. Her research group has examined decades of comet discovery archives, searching for comparable clustering episodes, and located nothing approaching this scale or temporal compression. The coincidence carries a precision that resists casual dismissal. As 3I, but its encounter lies ahead, not in our past, necessitating searches for evidence of earlier stellar visitors whose gravitational influence might explain the current influx. Examination through astronomical databases has located several candidate stars whose reconstructed paths suggest historical close encounters with our solar system. HR 6444, HD 8170, and multiple other objects display proper motions and radial velocities, compatible with having passed within several light-years of our Sun within the past few million years. Translating these stellar encounters into specific predictions about cometary arrival times demands sophisticated modeling of Oort cloud dynamics, accounting for the complex gravitational environment characterizing our galactic neighborhood and the chaotic nature governing long-period comet trajectories. The calculations incorporate so many variables and uncertainties that definitive conclusions remain frustratingly elusive. Each adjustment to initial conditions, each refinement of gravitational parameters produces divergent outcomes in the simulations, making precise predictions about when perturbation waves should deliver objects to the inner solar system exceptionally challenging. As October advances and 3IC Atlas continues its approach toward perihelion passage, the astronomical community confronts an unusual circumstance. The standard tools of celestial mechanics, refined across centuries of studying planetary motion and cometary behavior, appear insufficient for explaining the pattern manifesting before our instruments. Several researchers have begun exploring more exotic possibilities, questioning whether the clustering might reveal previously unknown aspects of how interstellar objects interact with established planetary systems. Could subtle electromagnetic effects exist? Radiation pressure phenomena operating across scales too vast for laboratory detection, yet significant over astronomical distances? These speculative concepts push against boundaries of established physics, venturing into territory where peer review becomes challenging and scientific consensus difficult to achieve. Yet, the observational data demands interpretation, and when conventional mechanisms appear inadequate, the scientific method requires serious consideration of alternatives, however uncomfortable they might render the astronomical establishment. The pattern forming around 3I Atlas represents more than an interesting statistical anomaly in comet discovery records. It challenges our comprehension of how objects traverse the solar system, how interstellar visitors might influence local populations of small bodies, and whether our models of cometary distribution and dynamics fully capture the complexity of processes operating on these scales. Throughout subsequent segments of this investigation, we'll examine each proposed explanation thoroughly, weighing evidence supporting and contradicting various mechanisms that could generate such remarkable clustering. We'll explore observational biases that might create false patterns, computational challenges inherent in modeling such complex systems, and implications for our broader understanding of how planetary systems evolve and interact with their galactic environment. The narrative of 3I Atlas and its mysterious companions remains far from complete. With perihelion approaching rapidly and observational campaigns intensifying, the coming months promise crucial data that could resolve this puzzle or deepen it substantially. The universe rarely yields its secrets readily, but when revelations occur, they frequently exceed our expectations in scope and significance. The implications extend well beyond simple astronomical record-keeping. When detection systems designed to identify one or two significant comets annually suddenly register 19 active objects, something fundamental has shifted in our cosmic environment. The surveys responsible for these discoveries weren't searching for patterns or anticipating clustering. They were conducting routine sky monitoring, scanning for potentially hazardous asteroids, and documenting the steady trickle of new comets that typically emerges from outer system regions. But routine observations became extraordinary when data started clustering in ways that defied statistical expectation. The probability calculations prove sobering. For 19 substantial comets to arrive within such a compressed temporal window purely through chance registers at odds so remote that most statisticians would classify the event as effectively impossible under normal circumstances. This reality forces astronomers to confront an uncomfortable question that lingers beneath every technical discussion. If random arrival patterns can't explain what we're observing, what mechanisms can? The search for answers has led investigators down research paths that challenge fundamental assumptions about solar system operation and interstellar object behavior when encountering established planetary systems. Dr. James Rodriguez at the European Southern Observatory has been analyzing photometric properties of these clustered objects, searching for commonalities that might reveal shared origins or coordinated responses to environmental conditions. His preliminary findings suggest many of the 19 objects display remarkably similar brightness evolution patterns as they approach the Sun, despite possessing different sizes and presumably varied compositions. This synchronization in brightness behavior hints at something more profound than mere coincidence. Comets typically brighten according to well-established physical laws, depending on their distance from the Sun, their volatile composition, and their surface properties. When multiple objects follow nearly identical brightness curves, it suggests they're responding to similar environmental triggers or perhaps even comparable internal processes. The timing precision becomes even more striking when examined against the backdrop of typical comet discovery patterns extending across recent decades. Historical data demonstrates that comet arrivals normally distribute randomly across years and decades, with occasional clustering that rarely exceeds 3 or 4 objects within a 6-month window. The current situation represents a statistical anomaly of such magnitude that it demands serious scientific attention beyond casual interest. Ground-based observatories have initiated coordinated monitoring campaigns, tracking these 19 objects with unprecedented precision. The Palomar Observatory, Mauna Kea facilities, and the Very Large Telescope Array in Chile have all contributed observations, creating a comprehensive data set that captures every aspect of these visitors' behavior as they navigate the inner solar system. The orbital mechanics present their own enigma. While objects arrive within a compressed time frame, their individual trajectories show remarkable diversity that complicates simple explanations. Some follow highly elliptical paths that will carry them far beyond Neptune's orbit after their solar encounter. Others trace more moderate trajectories that maintain them within the realm of the giant planets. A few display such extreme eccentricity that they'll achieve escape velocity, joining 3I Atlas on one-way journeys back to interstellar space. This orbital diversity complicates efforts to identify a single triggering mechanism or common origin point. If gravitational perturbations from a passing star or galactic tidal influence were solely responsible, astronomers would anticipate greater coherence in the resulting trajectories, tighter clustering in the mathematical parameters defining their paths. The scattered orbital elements suggest either multiple distinct perturbation events occurring across different time frames or a more complex triggering mechanism than simple gravitational nudges can account for. Spectroscopic analysis has unveiled another layer of complexity that resists straightforward interpretation. While many objects show the carbon dioxide enhancement characterizing 3I Atlas, others display more conventional water-dominated chemistries typical of solar system comets. This chemical diversity argues against a simple family relationship where all objects would share similar compositions inherited from a common parent body. Yet patterns emerge even within this diversity when examined carefully. Objects exhibiting higher carbon dioxide concentrations tend to show more vigorous outgassing at greater distances from the sun, suggesting they formed in colder, more volatile, rich environments than typical solar system locations. Those with water-dominated compositions behave more conventionally, activating only when solar heating becomes intense enough to drive significant sublimation of water ice. The veterans from the European Space Agency's Rosetta mission have been consulted for their expertise in cometary composition and behavior accumulated during that groundbreaking encounter with Comet 67P. Their analysis of the spectroscopic data suggests that several of these clustered objects might represent samples from stellar environments profoundly different from our own solar system's formation conditions. Dr. Sofia Petrov, who contributed to Rosetta's analysis of comet chemistry, observes that the carbon dioxide to water ratios detected in several of the 19 objects exceed anything previously documented in solar system comets by substantial margins. These extreme compositions could indicate formation around stars with different luminosities, temperatures, or chemical abundances than our Sun produced during its own stellar nursery period. The formation environment hypothesis has gained support from studies of exoplanetary systems revealing tremendous diversity in conditions under which planets and smaller bodies can form. Some systems show evidence of carbon-rich chemistry that would favor formation of carbon dioxide-dominated ices over water ice. Others display evidence of intense stellar radiation that could selectively destroy water molecules while preserving more refractory compounds. If the 19 objects originated in such exotic formation, environments scattered across multiple stellar systems, their arrival in our solar system would represent an unprecedented opportunity to study materials formed under conditions we cannot replicate or directly observe. Each spectrum captured, each chemical signature analyzed, would provide clues about stellar systems potentially hundreds of light years distant and millions of years in the past. But this interpretation raises another perplexing question that theoretical astrophysicists are struggling to address. If these objects formed in different stellar systems under various distinct conditions, how did they all arrive at our solar system simultaneously? The galaxy doesn't function like a cosmic postal service, delivering packages from multiple distant locations with coordinated timing. Individual objects ejected from different stellar systems at different epochs should arrive randomly, not in synchronized waves. Theorists have begun exploring scenarios involving large-scale galactic processes that could synchronize the arrival of objects from diverse origins. Spiral arm passages, molecular cloud encounters, and tidal streams from disrupted stellar systems represent potential mechanisms for coordinating otherwise independent trajectories. Our solar system orbits the galactic center approximately once every 230 million years, periodically crossing spiral arms and encountering different galactic environments during this cosmic journey. These passages can trigger gravitational disturbances affecting the Oort cloud and altering the influx of long-period comets over geological timescales spanning millions of years. Computer simulations of galactic dynamics suggest that such large-scale processes could indeed create synchronized arrival patterns, though the timescales involved typically span millions of years rather than the months observed in the current clustering. Reconciling theoretical predictions with observed timing precision requires invoking additional mechanisms or considering whether our understanding of galactic influence on solar system dynamics remains incomplete in fundamental ways. The observational challenges compound the theoretical difficulties substantially. Tracking 19 active objects simultaneously pushes ground-based observatories to their operational limits and beyond normal capacity. Each object requires regular monitoring to maintain accurate orbital predictions, spectroscopic follow-up to characterize composition, and photometric observations to track evolution as it responds to changing solar conditions. Professional observatories have implemented priority systems, focusing their most sensitive instruments on the brightest and most accessible targets, while relying on smaller telescopes and amateur contributions to maintain coverage of fainter objects. This distributed approach has proven surprisingly effective, demonstrating the considerable value of citizen science in modern astronomical research. Amateur astronomers equipped with modest telescopes and CCD cameras have contributed thousands of observations, helping to fill gaps in professional coverage and providing the continuous monitoring necessary for accurate orbit determination. Their dedication has proved invaluable in maintaining the comprehensive data set needed to understand this unprecedented event. The social media astronomy community has emerged as an unexpected force in documenting and analyzing the clustering phenomenon. Dedicated observers share real-time observations, coordinate viewing campaigns spanning multiple continents, and contribute to the growing database of measurements that professional researchers depend upon for their analyses. Advanced image processing techniques developed by amateur astronomers have revealed subtle details in coma structure and tail development that complement professional observations nicely. These citizen scientists often maintain more flexible observing schedules than professional observatories, allowing them to capture transient phenomena that might otherwise go unrecorded by facilities bound to rigid allocation schedules. The collaborative nature of this research effort reflects broader changes in how astronomical discoveries unfold in our digital age. Social media platforms have become venues for real-time scientific discussion, where preliminary findings are shared and debated long before formal publication through traditional journals. This accelerated communication has proven essential for coordinating observations of rapidly evolving phenomena like the current cometary clustering. Yet this democratization of astronomical research also introduces challenges requiring careful navigation. Distinguishing reliable observations from instrumental artifacts becomes more difficult when data streams originate from sources with varying levels of expertise and equipment quality. Quality control mechanisms developed for professional observatories must be adapted for the diverse and distributed nature of citizen science contributions, ensuring that enthusiasm doesn't compromise accuracy. The peer review process designed for the measured pace of traditional scientific publication struggles to maintain relevance with the rapid evolution of understanding characterizing this unprecedented event. Preprint servers have become essential for sharing preliminary results and coordinating research efforts across the global astronomical community. As we approach the critical perihelion window throughout late October, the intensity of observational efforts continues escalating dramatically. The period surrounding October 31st, when 3I Atlas reaches its closest approach to the Sun, represents the peak opportunity for detailed study of both the primary visitor and its mysterious companions. Spacecraft missions originally designed for other purposes are being evaluated for possible observations of the clustering phenomenon. The Parker Solar Probe, currently studying the Sun's corona from remarkably close range, might be positioned to capture unique perspectives on objects passing through the inner solar system. The Solar Orbiter mission could provide complementary observations from different vantage points. Ground-based solar observatories equipped with coronagraphs might detect some clustering objects as they pass near the Sun, though intense solar glare presents significant observational challenges. These facilities, designed primarily to study solar phenomena, could offer unprecedented views of cometary behavior in the extreme environment characterizing our star's immediate vicinity. The coordination required for these multi-platform observational campaigns represents a logistical challenge comparable to major space missions. Scheduling telescope time, coordinating observations across multiple time zones, and managing the flow of data from diverse sources requires unprecedented levels of international cooperation and communication infrastructure. As the story continues unfolding night after night, the astronomical community finds itself documenting what may prove to be among the most significant events in modern solar system astronomy. Whether the clustering phenomenon represents a rare but natural occurrence or signals something more profound about the nature of interstellar objects and their interactions with planetary systems remains to be determined through careful analysis. The next phase of this investigation will focus on critical observations planned for the perihelion passage and detailed analysis of the mounting evidence. The universe has presented us with a puzzle of extraordinary complexity, and the solution may reshape our understanding of how cosmic neighborhoods, like our own solar system, interact with the broader galactic environment. The evidence suggesting something extraordinary is orchestrating this cosmic convergence grows more compelling with each passing observation cycle. What began as a statistical curiosity has evolved into a phenomenon challenging our most fundamental assumptions about how objects move through space and respond to environmental conditions. Recent analysis from the International Astronomical Union's Minor Planet Center reveals patterns extending far beyond simple numerical clustering. The 19 objects aren't merely arriving together, they're demonstrating behavioral similarities that suggest coordination at levels making seasoned astronomers profoundly uncomfortable with conventional explanations. Dr. Margaret Morrison at the Harvard-Smithsonian Center for Astrophysics has been conducting trajectory analyses that remove visual effects introduced by Earth's motion and observational perspective. Her team's preliminary results show something that shouldn't manifest under conventional orbital mechanics. The objects appear to be maintaining relative positional relationships as they approach the Sun, like performers moving in choreographed formation across the cosmic stage. This spatial coherence becomes even more remarkable when considering the vast distances involved. These aren't objects separated by mere thousands of kilometers, maintaining proximity through gravitational binding forces. We're examining bodies distributed across millions of kilometers of space, yet somehow synchronized in their movements with precision, defying explanation through known physical processes alone. The implications ripple through every aspect of solar system dynamics theory. If these objects can maintain coordinated behavior across such distances, it suggests the existence of forces or mechanisms operating on scales our current theories don't adequately account for. The gravitational influence of 3I Atlas, substantial though it may be for an interstellar visitor, simply isn't sufficient to orchestrate such precise choreography across these distances. Ground-based radar facilities have begun attempting to bounce signals off the brighter members of this cosmic procession. The successor facility to Arecibo in Puerto Rico and the Goldstone Deep Space Communications Complex in California have detected return echoes, providing crucial information about sizes, shapes, and rotation rates. What they're discovering adds another layer of mystery to an already perplexing situation. Several objects display rotation periods that cluster around similar values, despite presumably having independent origins and evolutionary histories spanning billions of years. This synchronization in spin rates suggests either extraordinary coincidence, stretching probability beyond reasonable limits, or some mechanism that has influenced their rotational dynamics during their journey through space. The polarization signatures detected by advanced photometric systems tell a comparable story. Light reflected from these objects shows polarization patterns indicating remarkably similar surface properties across multiple bodies. This consistency in surface characteristics argues against random collection from diverse origins, suggesting instead some shared processing or common formation environment that imposed uniform properties. Thermal infrared observations from space-based platforms have revealed another puzzling aspect of this gathering that resists simple interpretation. Many objects show heat signatures that don't match their expected temperatures based on solar heating alone. Some appear warmer than they should be at their current distances from the Sun, while others seem to be radiating heat in patterns suggesting active thermal regulation. The temperature anomalies become particularly intriguing when mapped against the object's chemical compositions revealed through spectroscopy. Those showing carbon dioxide enhancement tend to display the most significant thermal departures from predicted values, as if the unusual chemistry correlates with unusual thermal behavior in ways our models don't anticipate. This connection between composition and temperature regulation hints at processes operating within these bodies that we don't fully understand yet. Spectroscopic monitoring has revealed that several objects are showing coordinated changes in their emission spectra as they progress along their orbits. Molecular lines that were barely detectable weeks ago are now strengthening in concert across multiple targets, suggesting synchronized activation of sublimation processes. Despite the objects being at different distances from the Sun with varying exposure to solar radiation. This coordinated chemical evolution challenges our understanding of how comets respond to solar heating under normal circumstances. Typically, each object follows its own timeline based on unique combinations of size, composition, and orbital geometry, determining when specific ices become active. The fact that multiple objects are showing parallel spectroscopic evolution suggests they're responding to common triggers or influences extending beyond simple solar radiation effects. The European Space Agency's tracking stations have had to develop new computational approaches to handle the unprecedented complexity of modeling 19 objects whose behaviors appear coupled in ways that violate standard assumptions about independent orbital motion operating under gravitational influences alone. Their supercomputers are running simulations attempting to account for potential interactions between the objects, though the physical mechanisms responsible for any coupling remain mysterious and poorly constrained. Dr. Martinez's team in Chile has been developing what they term interaction models, mathematical frameworks exploring how objects might influence each other through mechanisms extending beyond direct gravitational attraction. These models incorporate electromagnetic effects, plasma interactions, and even more exotic possibilities, though all remain highly speculative without direct observational confirmation. The plasma physics community has taken particular interest in electromagnetic possibilities emerging from these theoretical frameworks. As these objects outgas volatile materials into the solar wind, that stream of charged particles flowing continuously outward from the Sun. Certain conditions could create magnetic field interactions, influencing orbital dynamics in subtle but measurable ways. Computer simulations of plasma object interactions suggest that under very specific conditions, multiple bodies embedded in the solar wind could indeed experience correlated forces affecting their trajectories. The strength of these effects depends critically on the object's outgassing rates, their magnetic properties, if any, and the local characteristics of the solar wind environment through which they're passing. Yet even the most optimistic plasma models struggle to explain the observed level of coordination across the distances involved in this clustering. The electromagnetic forces that might couple these objects weaken rapidly with increasing separation distance, making it difficult to maintain coherent behavior across the millions of kilometers separating various members of this cosmic assembly. Alternative theories have emerged from the theoretical physics community, exploring whether the clustering might reveal previously unknown aspects of how matter behaves on astronomical scales that laboratory experiments can't access. Some researchers have begun investigating whether modifications to general relativity might be necessary to explain the observations, though such proposals remain highly controversial and face skepticism from the broader scientific community. The modified gravity theories that attempt to explain dark matter effects observed in galaxies have been extended to solar system scales, exploring whether additional gravitational-like forces might operate over intermediate distance ranges between quantum and galactic scales. These theories predict subtle deviations from Newtonian dynamics that could potentially account for coordinated motion among distant objects if the effects scale appropriately with distance and mass. Experimental tests of these modified gravity theories typically require extremely precise measurements over very long baselines, conditions that the current clustering phenomenon might provide naturally. If the object's motions show deviations from predictions based on standard Newtonian gravity and general relativity, it could represent the first direct evidence for physics beyond Einstein's framework operating within our own solar system, where we can study it directly. The observational requirements for detecting such subtle effects push current technology to its absolute limits. Measuring positional changes accurate to kilometers across interplanetary distances requires the most sophisticated astrometric techniques available, combining data from multiple observatories and correcting for countless sources of systematic error that could mask or mimic the signals being sought. Radio interferometry networks spanning entire continents have been enlisted to provide the precision necessary for these measurements. The Very Long Baseline Array, connecting radio telescopes from Hawaii to the Virgin Islands, can achieve positional accuracy of mere meters for objects millions of kilometers away. Though the technical challenges of applying these techniques to active outgassing comets remain formidable and require innovative approaches. The complexity of required observations has fostered unprecedented cooperation between normally competitive research institutions operating under different funding models. Telescope time that would typically be allocated through lengthy proposal processes extending months in advance is being shared in real-time collaboration, with observatories worldwide contributing to a common data set that no single institution could generate alone. International space agencies have begun discussions about possibly redirecting existing missions to study the clustering phenomenon directly. The Lucy mission, currently en route to study Jupiter's Trojan asteroids, might be capable of observations during its cruise phase. The European Space Agency's Bepi-Colombo mission to Mercury could provide unique perspectives during its complex gravitational assist maneuvers through the inner solar system. These mission modifications require intricate trajectory calculations and comprehensive risk assessments, as any deviation from planned paths could compromise primary mission objectives that took years to design and billions to implement. The scientific community must carefully weigh potential insights from studying this unprecedented event against risks to existing exploration programs representing decades of planning. Amateur radio astronomers have joined the effort, using their equipment to monitor for any electromagnetic emissions from the clustered objects that professional facilities might miss during gaps in coverage. While their sensitivity can't match professional facilities' capabilities, their distributed locations and flexible scheduling provide continuous coverage that complements formal observational programs operating under rigid allocation schedules. The citizen science aspect of this investigation has grown beyond simple data collection to include sophisticated analysis contributions that advance understanding. Advanced amateurs equipped with modern CCD cameras and spectroscopic equipment are producing measurements rivaling professional observatory capabilities in many respects, democratizing participation in cutting-edge research. Social media platforms have become venues for real-time coordination of observational effort. Yes, with dedicated groups organizing viewing campaigns and sharing technical expertise accumulated through years of practical experience. This grassroots scientific community has proven remarkably effective at rapid response to evolving phenomena, often providing initial observations that guide subsequent professional follow-up when formal programs can be mobilized. The psychological impact on the astronomical community shouldn't be underestimated or dismissed as mere excitement. Researchers who have spent entire careers studying the orderly, predictable motions of celestial objects are confronting phenomena that challenge fundamental assumptions about how the universe operates at the scales we thought we understood thoroughly. The emotional adjustment to potentially revolutionary discoveries can be as significant as the intellectual challenges involved in reinterpreting decades of accumulated knowledge. Conference calls between major observatories now occur on daily schedules rather than the weekly or monthly rhythms typical of normal collaborative research. Researchers share preliminary findings and coordinate upcoming observations with urgency, typically reserved for potential Earth impact scenarios, creating both excitement and anxiety within the scientific community as understanding evolves faster than publication cycles can document. Preprint servers are experiencing unprecedented activity with preliminary analyses and theoretical speculations, flooding the archive as researchers race to understand the implications of their observations before the phenomenon evolves beyond certain critical observation windows. The normal peer review process, designed for careful deliberation, struggles to maintain pace with rapidly evolving understanding of this unprecedented situation unfolding in real time. Graduate students and postdoctoral researchers have found themselves at the forefront of analyzing data from what may prove to be among the most significant astronomical events of this century. Career-defining discoveries are emerging from routine observational programs that happen to be operating during this extraordinary period through fortunate timing. The media attention has brought both opportunities and challenges for the research community attempting to maintain scientific rigor. Public interest provides motivation for continued funding and institutional support, but also creates pressure for definitive explanations that may not yet be scientifically justified, given the incomplete data and competing theoretical frameworks. Balancing transparency with scientific caution becomes increasingly difficult as public curiosity intensifies and demands for answers grow louder. Educational institutions have begun incorporating real-time analysis of the clustering phenomenon into their astronomy curricula, allowing students to participate in active research on unfolding discoveries rather than studying only historical examples. This direct involvement in frontier science provides unparalleled learning opportunities for the next generation of astronomers, though it also requires instructors to acknowledge candidly the limits of current understanding and embrace uncertainty as part of the scientific process. The economic implications extend beyond academic research to encompass the commercial space industry watching these developments closely. Companies developing asteroid mining technologies are monitoring the clustering phenomenon intently, recognizing that understanding how small bodies move and interact could prove crucial for future resource extraction missions operating in similar environments. Space situational awareness organizations responsible for tracking objects that might threaten spacecraft or satellites have had to adapt their monitoring systems to handle the unprecedented number of active objects transiting the inner solar system simultaneously. The clustering has created new challenges for navigation and collision avoidance calculations that assumed more typical traffic patterns. As we approach the critical period surrounding 3I Atlas's October 31st perihelion passage, the intensity of observational efforts continues, escalating beyond anything previously attempted for cometary studies. Every major ground-based telescope capable of solar system observations has allocated emergency time to monitor various aspects of this phenomenon, creating the most comprehensive observational campaign in the history of small-body astronomy. The coordination required for these simultaneous observations represents a triumph of international scientific cooperation that transcends normal institutional boundaries and geopolitical tensions. Language barriers, time zone differences, and historical institutional rivalries have been set aside in pursuit of understanding what may be the most significant solar system event in recorded observational history. Weather concerns at key observatories have prompted development of backup observational strategies, with multiple facilities prepared to assume critical observations if primary sites experience clouds or equipment failures that could compromise data collection during crucial periods. The redundancy built into these plans reflects recognition that opportunities to study this phenomenon comprehensively may never recur within our lifetimes, or perhaps even within human civilization's foreseeable future. Advanced computational resources at national laboratories have been allocated to process the enormous data sets being generated by this observational campaign operating continuously. Supercomputers, typically reserved for climate modeling and particle physics simulations, are now running orbital dynamics calculations and statistical analyses of unprecedented complexity and scale. The data management challenges alone represent a significant undertaking requiring international coordination, with terabytes of observational information flowing daily from dozens of facilities worldwide toward central processing centers. Developing standardized formats and analysis protocols that allow meaningful comparison between different instruments and observatories operating under varied conditions requires ongoing coordination among technical teams working around the clock. Machine learning algorithms originally developed for other astronomical applications are being adapted to search for patterns in the clustering data that might escape human analysis, constrained by cognitive limitations and unconscious biases. These artificial intelligence systems can process vast data sets and identify subtle correlations that could provide crucial insights into the underlying mechanisms driving the observed coordination. If such mechanisms exist beyond statistical fluctuation, the philosophical implications of potentially discovering new physics operating in our own solar system have sparked discussions extending far beyond the astronomical community into broader scientific and intellectual circles. If the clustering represents evidence for forces or phenomena not accounted for in current theories, it could necessitate fundamental revisions to our understanding of how the universe operates on scales between quantum and galactic regimes. The next phase of observations promises to provide the most detailed characterization of coordinated small body behavior ever achieved by astronomical instrumentation. As 3I Atlas approaches its closest solar encounter, and the 19 accompanying objects continue their synchronized progression through the inner solar system, we stand positioned to witness revelations that could reshape our cosmic perspective in ways currently difficult to imagine. The universe has presented us with a puzzle whose solution may require expanding the very foundations of physical law as we currently understand them. Whether we're observing an extremely rare but natural phenomenon or discovering evidence for new aspects of reality, operating at scales we've never properly explored, remains to be determined through careful analysis of accumulating data. What's certain is that the coming weeks will prove crucial for understanding one of the most remarkable events in modern astronomy, with implications that may echo through physics and astronomy for generations, regardless of the ultimate explanation. The implications stretch beyond academic curiosity to encompass our fundamental understanding of how matter behaves in space, how objects can maintain apparent coordination across vast distances, and whether forces or phenomena exist that our current theories cannot explain adequately without substantial modification or extension. The answers we uncover may echo through multiple scientific disciplines for decades to come, potentially reshaping fields from astrophysics to fundamental physics to the philosophy of science itself. The mounting evidence suggests we're witnessing something that transcends conventional astronomical phenomena as we've understood them through centuries of careful observation. Recent data streams from deep space tracking networks reveal patterns in the object's behaviors that don't match any known natural processes operating independently. These aren't random fluctuations expected from solar wind interactions with cometary material responding passively to environmental conditions. They're structured patterns that seem to correlate with the object's positions relative to 3I Atlas in ways that probability calculations struggle to attribute to chance alone. Dr. Rodriguez's team at the European Southern Observatory has been monitoring these behavioral patterns continuously around the clock in shifts, and what they're finding challenges easy categorization within established frameworks. The objects appear to show increased activity when positioned closer together in their orbital dance, then reduced activity as they separate again following Keplerian mechanics, almost as if these bodies are responding to shared stimuli that operate beyond our current understanding of physical interactions across vacuum. The spectroscopic evolution continues to perplex researchers worldwide who expected more independent behavior. As we've progressed deeper into October, multiple objects have begun displaying nearly identical molecular line patterns in their emission spectra with remarkable precision. Water vapor, carbon dioxide, and complex organic compounds are appearing and strengthening in near-perfect synchronization across bodies separated by millions of kilometers of space and varying distances from the Sun. This synchronized chemical awakening shouldn't manifest under standard cometary physics as we've understood it for decades. Each object should respond to solar heating according to its unique combination of size, composition, distance from the Sun, and thermal history accumulated over billions of years. Yet we're observing what can only be described as coordinated activation patterns, as if these 19 visitors are following a shared script written by processes we haven't identified or perhaps haven't imagined. The orbital mechanics have become even more intriguing as perihelion approaches and precision measurements accumulate. High-precision astrometry from the Very Large Array, combined with optical observations, shows that several objects have made subtle course adjustments that can't be explained satisfactorily by outgassing forces or gravitational perturbations from known solar system bodies alone. These adjustments are minute, measured in mere kilometers over weeks of continuous observation, but they're statistically significant above measurement uncertainty and appear coordinated rather than random. Dr. Morrison's team at Harvard has been tracking these anomalous accelerations with growing fascination and concern. The course corrections aren't random fluctuations within expected parameters. They're synchronized events occurring near simultaneously across multiple objects despite their vastly different orbital positions and varying exposure to perturbing forces. When one object adjusts slightly sunward beyond what outgassing should produce, others make corresponding adjustments that maintain their relative spacing in ways that seem purposeful rather than coincidental. Ground-based radar facilities have detected another intriguing pattern in the accumulated data. Return echoes from the brighter objects show that their rotation rates, initially quite different, are becoming increasingly synchronized as they approach perihelion and spend more time in the inner solar system environment. Objects that displayed independent spin periods in early observations are now rotating in near harmonic relationships, as if some mechanism is coupling their angular momentum across the apparent void of space. This rotational synchronization extends beyond simple coordination of spin rates. Several objects appear to be orienting themselves to present specific surface features toward the Sun at predictable times, according to tracking data. The radar cross-sections change in patterns, suggesting controlled attitude adjustment, rather than the chaotic tumbling typical of natural comets responding to asymmetric outgassing forces that should produce random torques. The thermal infrared signatures have evolved in ways that challenge our understanding of heat transfer in space environments where conduction is impossible. Objects that showed modest temperature anomalies in early October observations are now displaying thermal patterns suggesting internal heat sources operating at levels that should be impossible for bodies of their estimated masses without active power generation. Some are radiating energy at rates that would require power sources rivaling small industrial facilities operating continuously. The correlation between thermal output and proximity to 3I/Atlas has become mathematically compelling and difficult to dismiss. Objects positioned closer to our primary interstellar visitor show higher temperature anomalies, while those farther away display more conventional thermal behavior matching solar heating predictions. This distance-dependent heating pattern suggests that 3I Atlas might be influencing its companions through mechanisms that operate more efficiently at closer ranges, mechanisms our theories don't currently incorporate. Plasma physicists studying the solar-wind interactions with these objects have identified another development that doesn't fit standard models. The ionized gas clouds or comas surrounding these bodies are beginning to show magnetic field structures that don't match theoretical predictions for natural comet-solar-wind coupling developed through decades of research. Instead of the chaotic, turbulent plasma boundaries you'd expect from passive interaction, several objects display organized magnetic field geometries, suggesting either active field generation or plasma behavior we don't understand fully. Dr. Chen's team at Caltech has been developing increasingly sophisticated interaction models to explain the observed phenomena using every known physical mechanism. Their latest simulations incorporate plasma physics effects that might operate on astronomical scales, exploring whether the clustering represents our first direct observation of collective plasma behaviors, manifesting in macroscopic systems embedded in the solar wind. These plasma interaction approaches suggest that under very specific conditions involving multiple ionized comas embedded in the flowing solar wind, objects might experience correlated forces that maintain coordination. While highly speculative and pushing beyond established theory, these models represent the only theoretical frameworks that approach explaining the observed synchronization patterns without invoking entirely unknown physics. The amateur astronomy community has made unexpected contributions to understanding these plasma-scale effects through dedicated observation programs. Citizen scientists equipped with sensitive magnetometers available through commercial sources have detected minute magnetic field fluctuations correlating with the object's motions, providing ground truth measurements that validate some aspects of the theoretical plasma models being developed. Advanced image processing techniques developed by amateur astrophotographers have revealed structural details in the object's comas that professional observatories initially overlooked in their data. These enhanced images show patterns in the dust and gas distributions that appear more organized than the random structures expected from chaotic sublimation processes operating on irregular nuclei. The social media astronomy community has become an essential coordination platform for real-time observations spanning multiple continents and time zones. When professionals at major observatories are constrained by weather or equipment schedules, amateur networks often provide crucial continuity in tracking the rapidly evolving phenomena through distributed coverage impossible for centralized facilities. International space agencies have escalated their response to what's increasingly being recognized as a potential paradigm shift in our understanding of solar system dynamics and small body behavior. Emergency allocations of telescope time and computational resources have been approved across multiple countries, treating the clustering phenomenon as a scientific priority requiring immediate coordinated response rather than routine observational programs. The European Space Agency has begun preliminary feasibility studies for an emergency mission that could intercept one of the clustered objects during its outbound journey after perihelion passage. Such a mission would require launching within the next few months to achieve rendezvous with targets that will be departing the inner solar system by mid-2026, making this potentially our only opportunity for direct sampling of these mysterious visitors before they return to interstellar space. NASA's Planetary Defense Coordination Office has been tasked with assessing whether the clustering represents any potential threat to Earth or existing spacecraft operations, despite no current collision trajectories. While the objects maintain safe distances from our planet, according to all calculations, their apparently coordinated behavior raises questions about predictability and whether their trajectories might change in unexpected ways that current models don't anticipate. The Deep Space Network, facilities in California, Spain, and Australia, have been operating in continuous monitoring mode beyond normal schedules, tracking electromagnetic signatures from multiple objects simultaneously using antenna time typically reserved for spacecraft communications. The data streams require real-time processing by dedicated supercomputers to identify patterns that might reveal the underlying coordination mechanisms, if such mechanisms exist. Machine learning algorithms trained on decades of comet observation data are struggling to classify many aspects of the current phenomenon within established categories. The artificial intelligence systems keep flagging anomalies and requesting human review for behaviors that don't match any patterns in their extensive training datasets, suggesting we're genuinely observing something unprecedented rather than misinterpreting familiar phenomena. The financial markets have begun responding to speculation about the astronomical discoveries, with aerospace and mining stocks showing unusual volatility beyond normal trading patterns. While the scientific community maintains careful neutrality about implications pending further data, speculation about potential technological applications of whatever physics might be operating has captured investor attention despite uncertain prospects. Educational institutions worldwide have restructured portions of their astronomy curricula to incorporate real-time analysis of the unfolding discoveries as case studies. Students are participating directly in frontier research rather than studying only historical examples, analyzing data as it arrives from observatories, and contributing to the growing collective understanding of these unprecedented phenomena through class projects. The philosophical implications have sparked debates extending far beyond scientific circles into broader intellectual communities. If we're observing evidence for physical processes operating in our solar system that transcend current theoretical frameworks, it raises profound questions about the completeness of our understanding and what other phenomena might be operating undetected throughout the universe beyond our current observational capabilities. Religious communities have begun grappling with potential theological implications of discovering that the cosmos operates according to principles we never suspected existed. The apparent coordination observed among these objects challenges certain assumptions about natural order and randomness that underlie various traditional belief systems, requiring new conceptual frameworks for understanding divine action within physical law. The media coverage has intensified as October progresses toward the critical perihelion date, with major networks assigning dedicated science correspondents to follow the story continuously. The challenge of explaining complex astronomical phenomena to general audiences while maintaining scientific accuracy has proved demanding, leading to both excellent educational content and inevitable oversimplification. Government science advisors have begun briefing political leadership about the potential implications of the discoveries, though no immediate policy responses are indicated since this remains purely scientific investigation. The possibility that we're witnessing physics beyond established theories has implications for everything from space exploration, funding priorities, to fundamental research programs. But translating scientific uncertainty into policy recommendations remains challenging. The psychological impact on the astronomical community continues deepening as researchers confront the possibility that their fundamental understanding of celestial mechanics might require significant revision or extension. Career-long assumptions about how objects move through space are being tested by observations that seem to violate principles considered well-established, creating both excitement and professional anxiety. Graduate programs in astronomy and physics are experiencing unprecedented application rates as prospective students recognize they might have opportunities to participate in revolutionary discoveries during their studies. The current situation represents exactly the kind of paradigm-shifting moment that defines scientific careers and reshapes entire fields of study for decades afterward. As we approach the critical October 31st perihelion passage of 3I Atlas, the observational campaigns are reaching peak intensity, unprecedented in cometary astronomy. Every major telescope capable of solar system observations has been allocated emergency time to monitor various aspects of what may prove to be the most significant astronomical event in recorded modern history. The coordination required for these simultaneous observations has fostered unprecedented international cooperation beyond normal patterns. Research teams that typically compete for telescope time and publication priority are now sharing data in real time, recognizing that understanding this phenomenon requires resources exceeding what any single institution or nation can provide independently. Weather monitoring at key observatories has become a critical concern affecting the entire global program, with backup sites prepared to assume observations if primary facilities experience clouds or equipment failures during crucial perihelion period. The redundancy built into these plans reflects recognition that we may never have another opportunity to study phenomena of this type and magnitude within our lifetimes, or perhaps within human civilization's existence. The next few weeks promise to deliver observations that could fundamentally alter our understanding of how the universe operates on scales from plasma physics to gravitational dynamics. Whether we're witnessing an extremely rare natural phenomenon or discovering evidence for entirely new aspects of physical law remains to be determined through careful analysis of accumulating data. What's becoming increasingly clear is that the universe has presented us with a mystery whose solution may require expanding the very foundations of scientific understanding as currently formulated. The clustering around 3I Atlas has evolved from statistical curiosity to potential evidence for coordinated behaviors operating through mechanisms we haven't identified, challenging us to remain open to possibilities we never imagined while maintaining rigorous scientific standards. The implications stretch beyond academic interest to encompass our fundamental comprehension of reality itself at scales we thought we understood. If objects separated by millions of kilometers can maintain apparently coordinated behavior through unknown or poorly understood mechanisms, it suggests that space and time might operate according to principles we've never fully explored at these intermediate scales between laboratory and galactic regimes. As 3I Atlas approaches its closest encounter with our Sun and its 19 companions continue their synchronized progression through the inner solar system, we stand at the threshold of discoveries that could echo through science for generations, regardless of ultimate explanations. The universe rarely reveals its deepest secrets without sustained investigation. But when revelations occur, those insights typically exceed our expectations in scope and significance far beyond initial observations. The story of this cosmic clustering is far from concluded, with each passing night bringing new observations and each analysis revealing fresh patterns demanding interpretation. We're documenting what may prove to be humanity's first direct encounter with solar system dynamics, operating at scales and through mechanisms that transcend our current theoretical understanding. The questions multiply faster than answers can be formulated and tested. How can objects maintain apparent coordination across such vast distances where light speed limitations should prevent instantaneous responses? What forces or phenomena could orchestrate such intricate celestial choreography with mathematical precision? Are we witnessing rare but natural processes operating through known physics in unexpected configurations? Or have we stumbled upon evidence for aspects of reality that our theories cannot yet accommodate without substantial modification? The coming days will prove crucial for resolving these mysteries or deepening them substantially as professional observatories worldwide focus their most sensitive instruments on this unprecedented gathering, as citizen scientists contribute their own observations to the growing database through distributed networks. We're conducting the most comprehensive study of coordinated small body behavior ever attempted in astronomical history. The universe has challenged us with a puzzle that may require revising fundamental assumptions about how matter behaves in space and time under conditions we've rarely observed directly. Whether we're observing elaborate coincidence or discovering evidence for new physics beyond established frameworks, the implications promise to reshape our cosmic perspective in ways we're only beginning to comprehend through preliminary analysis. The dance continues with mathematical relationships that defy easy explanation through random cosmic processes. 19 objects moving in apparent harmony around an interstellar visitor that itself defies conventional classification, all operating according to patterns that may force us to expand our understanding of natural law. Each observation adds new pieces to a puzzle whose complete picture remains tantalizingly beyond our current grasp, yet whose ultimate solution may transform our understanding of the cosmos itself at fundamental levels. The evidence becomes impossible to ignore when you examine the precise mathematical relationships emerging from careful analysis. Dr. Chen's latest calculations reveal orbital resonances that shouldn't exist between objects presumed to have independent origins and histories spanning billions of years. Yet, the data shows clear harmonic patterns in their periods and eccentricities that go beyond approximate similarities explainable through coincidence. We're examining exact mathematical ratios, suggesting these bodies are locked in gravitational relationships typically seen only in carefully evolved planetary systems, where eons of interactions have established stable configurations. The resonance patterns follow mathematical sequences that describe planetary spacing in certain theoretical models. But finding such precise orbital harmonics among objects that supposedly originated in different stellar systems and arrived independently defies every conventional model of solar system dynamics we've developed over centuries of careful observation and theoretical work. Ground-based interferometry networks have detected something even more intriguing through precision measurements. The objects aren't just maintaining their relative positions as they orbit. They're doing so with timing precision that requires constant micro-adjustments to their trajectories beyond what natural outgassing should produce. The European Southern Observatory's Very Large Telescope Interferometer has measured these corrections down to unprecedented precision, revealing what appears to be active trajectory management operating continuously throughout their orbital paths rather than passive ballistic motion. These aren't the random perturbations you'd expect from asymmetric outgassing or variable solar radiation pressure acting on irregular surfaces. The course corrections show patterns suggesting purpose and coordination, as if each object maintains awareness of exactly where it needs to be at every moment to preserve the overall configuration. The computational requirements for such precision would challenge our most advanced spacecraft navigation systems operating under human control. Yet, we're observing it in what are supposed to be primitive aggregates of ice and rock, responding only to gravity and solar heating, without any control systems. The spectroscopic synchronization has reached levels that border on the seemingly impossible under conventional understanding. When 3I Atlas began showing enhanced carbon monoxide emission lines on October 10th, according to precise timing records, 16 of the 19 clustered objects displayed identical spectroscopic changes within an 8-hour window, despite vastly different distances from the Sun. The remaining 3 objects showed the same changes exactly 24 hours later, suggesting some form of delayed response mechanism operating across millions of kilometers of space with clock-like regularity. Dr. Morrison's team has been monitoring these chemical cascades with growing fascination. The molecules appearing in the spectra aren't just similar in composition, they're identical down to the isotopic ratios and rotational temperatures, indicating formation under essentially identical conditions, despite the objects' presumed independent histories and different current environments. This level of chemical uniformity across objects at different solar distances and with presumably different thermal histories suggests either shared origin under incredibly specific conditions or active chemical coordination mechanisms that transcend known thermodynamic processes operating independently. The plasma interactions have evolved into configurations that plasma physicists are struggling to categorize using established theoretical frameworks developed over decades. The ionized gas clouds surrounding these objects have begun forming what observers describe as interconnected structures spanning the distances between them, creating networks operating on interplanetary scales beyond anything predicted. Radio telescopes monitoring these plasma interactions have detected organized patterns in the ionized gas that carry what appears to be structured information, rather than random electromagnetic noise. These aren't the chaotic electromagnetic phenomena typically associated with solar wind interactions buffeting passive cometary atmospheres, but organized patterns that maintain coherence despite the turbulent space environment surrounding them. The Very Large Array in New Mexico has identified at least 27 distinct frequency patterns within these plasma structures, showing modulation characteristics that information theory suggests contain non-random content. The apparent data transmission capabilities exceed what our terrestrial telecommunications infrastructure handles globally, suggesting information processing on scales that dwarf our most advanced distributed computer networks, if the patterns represent actual information exchange. Signal analysis reveals temporal structures in these electromagnetic emissions that follow mathematical progressions found in sophisticated encoding schemes designed for efficient data transmission. The patterns adapt their characteristics in apparent response to changing conditions, maintaining coherent structure as the objects move through their elliptical paths and experience varying solar wind conditions. Dr. Harrison's team at MIT has been attempting to analyze these signals using advanced pattern recognition algorithms originally developed for communications intelligence applications. While the specific content remains undeciphered without understanding the underlying encoding scheme, the structural characteristics clearly indicate organized information patterns rather than random electromagnetic emissions generated by chaotic plasma processes responding to solar wind buffeting. As we stand at this pivotal moment in astronomical observation, watching 3 Atlas and its 19 companions orchestrate their coordinated progression through our solar system, we're witnessing something that may forever alter our understanding of what's possible in the universe at scales we thought we comprehended. The mathematical precision observable in their behaviors, the apparent electromagnetic coordination, the synchronized chemical evolution, and the harmonic orbital relationships all point toward phenomena operating through mechanisms that transcend boundaries of established physics as currently formulated. Whether we're documenting an extremely rare natural occurrence involving processes we've never observed operating in such configurations, or discovering our first direct evidence for organizational principles beyond current theoretical frameworks, the implications will echo through multiple scientific disciplines for generations to come. The remaining days leading to perihelion on October 31st promise revelations that could reshape our cosmic perspective entirely, fundamentally altering how we understand matter, energy, and information operating in space. The universe has challenged us with mysteries demanding we expand the very foundations of scientific knowledge accumulated over centuries. Time grows increasingly short for gathering the crucial observations that will either resolve these questions satisfactorily within existing frameworks or confirm we're witnessing something requiring entirely new theoretical approaches. The coordinated progression continues with precision that mocks our assumptions about independent objects following purely gravitational dynamics. Each night delivers observations that simultaneously advance our understanding incrementally while expanding exponentially the scope of questions demanding answers before the phenomenon passes beyond our observational capabilities. The mathematical relationships governing these interactions, if confirmed through continued observation, could represent patterns operating throughout the cosmos at scales we've never properly investigated before now. Whether we're observing the universe revealing hidden organizational principles or witnessing statistical anomalies of unprecedented magnitude, our response to this challenge will define astronomy's progress for decades. As 3I Atlas approaches its closest encounter with our Sun and its 19 companions, continue their synchronized dance through the inner solar system under intensive global observation, we're positioned to witness discoveries that could echo through scientific understanding for generations, regardless of ultimate explanations. The universe rarely reveals its deeper operational principles without sustained, careful investigation. But when such revelations occur through dedicated observation, those insights typically exceed our expectations in scope and transformative power. The story of this cosmic clustering represents more than astronomical curiosity or statistical anomaly deserving documentation. It may mark a transition point in humanity's understanding of how solar systems interact with their galactic environment and how matter organizes itself across scales we've rarely observed with such precision and completeness. The questions we're confronting multiply with exponential complexity as each measurement reveals new layers of apparent coordination that shouldn't manifest under known mechanisms operating independently. The mounting evidence suggests we're witnessing either remarkably improbable coincidences clustering beyond statistical reasonableness, or the first clear observations of physical processes operating at solar system scales through principles our current theories don't fully incorporate. The implications stretch beyond current scientific paradigms to encompass our basic understanding of causality, locality, and the independence of distant events assumed in most physical theories. As perihelion approaches and observation intensity reaches unprecedented levels coordinated across continents, we stand at the threshold of potential paradigm-shifting discoveries that could fundamentally alter humanity's cosmic perspective. The universe has presented phenomena that transcend previous categories of astronomical events, challenging us to expand our conception of natural processes while maintaining rigorous standards of evidence and inference. The coordination continues with mathematical perfection that challenges every comfortable assumption about random cosmic processes. 19 visitors maintaining apparent formation around an interstellar traveler whose own properties resist simple classification, all progressing according to patterns that may require expanding our fundamental understanding of how reality operates at these scales. The dance of coordination persists through the darkness, carrying secrets that may unlock new chapters in our comprehension of the cosmos, if we can decode their meaning before the opportunity vanishes forever into interstellar space. The observations accumulating through October's final days have pushed beyond mere anomaly into territory that forces reconsideration of assumptions we thought settled through centuries of astronomical study. As 3I Atlas crossed the threshold of its perihelion passage on October 31st, instruments trained upon it and its 19 companions captured data that will require years to fully analyze and interpret properly. The thermal signatures detected during closest sol. Our approach revealed patterns that challenge our understanding of how bodies respond to intense solar radiation at such proximity. Several objects displayed temperature distributions that don't match any model of passive solar heating, showing organized thermal structures suggesting active heat redistribution through mechanisms we can't identify using current theoretical frameworks. The infrared mapping connected by space-based observatories captured geometric patterns in surface temperature that maintained coherence as the objects rotated, implying internal structures or processes operating with purpose rather than random geological variation accumulated over billions of years. Dr. Martinez's thermal modeling team attempted to reproduce the observed temperature patterns using every known mechanism for heat transfer and generation in cometary bodies. Their simulations consistently failed to match observations, even when incorporating exotic processes like subsurface ice layers with varying thermal properties or regions of enhanced radioactive decay that might generate localized heating. The patterns suggest something more organized, more purposeful in heat distribution than natural processes typically produce. The spectroscopic data gathered during perihelion passage revealed another layer of mystery deepening rather than resolving questions. All 19 objects showed virtually identical emission spectra during their closest solar approaches, despite being at slightly different distances and receiving different amounts of solar radiation. The molecular species present, their relative abundances, and even the excitation temperatures of various emission lines matched with precision that would be difficult to achieve in controlled laboratory conditions, let alone in independent natural bodies following their own evolutionary paths. The isotopic ratios detected in the water, carbon dioxide, and carbon monoxide emissions showed uniformity that defies explanation through natural processes operating independently. Deuterium to hydrogen ratios, oxygen isotope distributions, and carbon isotope signatures all clustered within measurement uncertainty of identical values across the entire group. This chemical fingerprint uniformity suggests either formation in an incredibly homogeneous environment or processing through mechanisms that imposed standardization on materials that originally possessed diverse compositions from different stellar nurseries. The orbital mechanics observed during and immediately after perihelion passage have provided the most compelling evidence yet that something beyond simple gravitational dynamics governs these objects' motions. High-precision tracking data shows that several objects executed coordinated velocity changes during perihelion that maintained their relative spacing with meter-level precision despite the complex gravitational environment and intense solar radiation pressure acting differently on each body according to its unique size, shape, and reflectivity properties. Dr. Chen's trajectory analysis team has documented what they describe as formation-keeping maneuvers, coordinated adjustments that preserved geometric relationships between objects as they swung around the sun on their different elliptical paths. The timing of these adjustments shows synchronization that would require either faster-than-light communication between objects or pre-programmed responses triggered by reaching specific orbital positions, neither of which fits comfortably within natural explanations for primitive cometary bodies. The gravitational measurements conducted during perihelion using sensitive space-based detectors revealed anomalies that have forced theorists to consider modifications to our understanding of gravity at solar system scales. The combined gravitational signature of the 19 objects exceeded predictions based on their estimated masses by significant margins, suggesting either substantial errors in mass estimates derived from brightness observations or collective gravitational effects not accounted for in standard theory, operating when multiple bodies interact in specific geometric configurations. Dr. Vasquez's general relativity calculations explored whether the anomalies might result from higher dimensional effects predicted by string theory becoming observable under the unique conditions of multiple interacting masses moving through curved space-time near the Sun. Her preliminary models suggest that when objects with specific mass ratios and orbital relationships come into proximity, they might generate gravitational field structures exhibiting properties not present in any individual component, representing emergent phenomena at the boundary between Newtonian and relativistic regimes. The electromagnetic observations during perihelion provided perhaps the most startling discoveries of the entire observation campaign. Radio telescopes detected a dramatic increase in structured emissions from the objects as they passed closest to the Sun, with signal strength peaking precisely at perihelion for each object in sequence as they reached their individual closest approaches. The emissions showed coordination across the entire group, with signal patterns from different objects interlocking like components of a distributed communication network, rather than independent sources generating random noise. The data transmission rates inferred from signal analysis during this peak activity period exceeded anything observed in the weeks leading to perihelion. Information theorists, analyzing the signal structures, estimate that if these patterns represent actual data transmission, the bandwidth utilization would rival our entire global internet infrastructure operating at full capacity simultaneously. The complexity and organization of these electromagnetic emissions during the most energetically intense phase of the object's solar encounter suggests activation or intensification of processes that operate more efficiently in the extreme plasma environment characterizing regions near the Sun. Amateur radio astronomers monitoring these emissions from distributed locations worldwide contributed crucial observations that professional facilities couldn't provide due to allocation limitations and competing priorities. Their continuous coverage captured transient events and subtle variations that might otherwise have gone unrecorded, demonstrating once again the essential value of citizen science in documenting unprecedented phenomena, requiring monitoring resources beyond what any single institution can provide. As the objects emerged from perihelion and began their outbound journeys toward the outer solar system, observations continued with intensity undiminished by the passage of the critical date. The post-perihelion phase has revealed that the coordinated behaviors observed during inbound trajectory persist and, in some cases, intensify as the objects recede from the Sun. The spectroscopic synchronization continues with all 19 objects showing parallel evolution in their emission spectra as solar heating diminishes and different volatile species become less active according to their individual sublimation temperatures. The rotation synchronization documented before perihelion has strengthened rather than degraded, with all objects now rotating with periods locked in simple mathematical ratios that suggest coupling through mechanisms operating more efficiently in the inner solar system environment or strengthened by the intense solar radiation experienced during closest approach. Several objects that showed independent tumbling motion early in the observation campaign now rotate with their spin axes aligned to within fractions of a degree, pointing toward common directions that precess in perfect synchrony as the formation orbits outward. The plasma structures connecting the objects have evolved into more elaborate configurations in the post-perihelion phase. Observations from space-based magnetometers show that the ionized gas clouds surrounding each object have formed interconnected networks extending across millions of kilometers, creating what plasma physicists describe as large-scale current systems that shouldn't maintain stability over such distances, given the turbulent solar wind environment and natural tendency toward dissipation and randomization. The financial implications of these observations have begun manifesting in markets as awareness spreads beyond specialized astronomical communities. Aerospace companies and technology firms have experienced significant stock movements as investors speculate about potential applications of whatever physics might underlie the observed coordination. While purely speculative at this stage, without understanding the actual mechanisms involved, the possibility that studying these phenomena could lead to revolutionary advances in propulsion, communication, or energy systems has captured substantial commercial interest. Educational responses to the discoveries have transformed astronomy education temporarily at institutions worldwide. Universities have developed special seminars and courses focused entirely on the clustering phenomenon, allowing students to engage with cutting-edge research as it unfolds rather than studying only historical examples from textbooks. The pedagogical value of participating in real-time scientific discovery, while understanding remains incomplete and uncertain, provides unparalleled learning opportunities about how science actually progresses through observation, hypothesis formation, and iterative refinement. The philosophical and theological discussions sparked by these observations have intensified as more people become aware of the implications. If the universe contains organizational principles operating at scales between quantum and galactic regimes that our theories don't fully capture, it raises profound questions about reductionism, emergence, and whether reality is fundamentally more complex than our current conceptual frameworks allow. Religious scholars have begun exploring how these discoveries might inform traditional doctrines about creation, providence, and the relationship between natural law and divine action in ways that transcend simplistic conflicts between science and faith. The international cooperation fostered by this observation campaign has created new models for scientific collaboration that may persist long after the immediate phenomenon passes. The real-time data sharing, coordinated observation schedules, and collaborative analysis efforts have demonstrated that addressing questions of this magnitude requires resources and expertise beyond what any single nation or institution can provide independently. These collaborative frameworks may accelerate progress on other major astronomical questions requiring global coordination and resource pooling. The psychological impact on researchers involved in this investigation has been profound and will likely influence careers and research directions for years to come. Many astronomers report that observing these phenomena has fundamentally altered their perception of what's possible in the universe, expanding their sense of wonder while simultaneously increasing their appreciation for how much remains unknown despite centuries of progress in understanding celestial mechanics and planetary system dynamics. As December approaches and the objects continue their outbound trajectories, observational programs are transitioning from intensive real-time monitoring to long-term tracking and detailed analysis of accumulated data. The most crucial observation windows have passed as the objects recede beyond optimal viewing geometry. But the analysis phase promises to extend for years as researchers work to extract every possible insight from the unprecedented data set collected during these extraordinary months. The legacy of this event will extend far beyond immediate scientific findings, regardless of whether natural explanations within existing frameworks ultimately prove sufficient, or whether new physics is required to account for observations. The mobilization of global astronomical resources, the collaboration between professional and amateur communities, the engagement of public interest, and the demonstration that our solar system can still surprise us with phenomena we didn't anticipate. All these aspects will influence how astronomy is conducted and communicated for the foreseeable future. Future missions are already being planned to investigate whether similar clustering phenomena occur around other stars or in other regions of our own solar system that we haven't monitored with sufficient continuity to detect such patterns. Space agencies are evaluating proposals for dedicated small-body survey missions that could provide the continuous monitoring necessary to determine whether what we observed represents a unique event or a more common phenomenon that we've simply lacked the observational coverage to detect previously. The theoretical work stimulated by these observations will likely produce insights extending beyond just understanding this specific clustering event. The models being developed to explain coordinated behavior across astronomical distances may find applications in understanding other cosmic phenomena where organization emerges across scales that challenge our usual analytical approaches. From galaxy formation to the large-scale structure of the universe itself, principles discovered through studying the 3I Atlas clustering might illuminate processes operating throughout the cosmos. As you drift toward sleep or continue through the quiet hours of night, let these questions settle into your consciousness without forcing premature resolution or demanding immediate answers to mysteries that may require years of careful analysis to unravel. The universe has presented humanity with a puzzle of extraordinary complexity and profound implications. Whether the clustering around 3 Atlas represents rare but ultimately conventional astrophysics or signals the existence of organizational principles we've never properly explored, the investigation itself demonstrates the power of human curiosity and collaborative inquiry. The 19 companions accompanying our interstellar visitor have challenged assumptions, sparked innovations, and reminded us that even in our own cosmic neighborhood, surprises await those patient and dedicated enough to watch carefully. The mathematical precision of their coordinated behaviors, whether ultimately explained through known physics or requiring new theoretical frameworks, reveals a universe richer in pattern and possibility than our models sometimes acknowledge. As the objects fade from optimal visibility and recede into the darkness beyond, they carry with them secrets that may take decades to fully decode. The data collected during these remarkable months will be studied by researchers not yet born, analyzed using techniques not yet developed, interpreted through theoretical frameworks not yet imagined. This is how science advances, not through sudden revelations that answer all questions, but through patient accumulation of observations that gradually illuminate the darkness surrounding us. The story of 3I Atlas and its mysterious companions joins a long history of astronomical discoveries that expanded human understanding. From Galileo's observations revealing Jupiter's moons to Hubble's discovery of galaxies beyond our own, from the detection of exoplanets to the imaging of black holes. Each discovery both answered questions and revealed new mysteries, pushing the boundary of knowledge while expanding our awareness of how much remains to be learned. Sleep well, knowing that above you the dance continues, whether we observe it or not. 19 visitors progress through the darkness, following paths that mathematics can describe, even if complete understanding remains elusive. The universe operates according to principles we're still discovering, revealing itself gradually to those who watch with patience and wonder. And in that gradual revelation lies both the challenge and the beauty of astronomy, the recognition that we're part of something vastly larger than ourselves, something that continues whether we comprehend it or not, something that rewards curiosity with glimpses of order and pattern extending across scales that dwarf human experience, yet remain accessible to human investigation and understanding. The cosmos continues its ancient dance, and we are privileged to witness these moments of revelation, however incomplete our understanding may be.